Welcome to a day in the life of a vSAN I/O, otherwise known as the last session of VMworld 2017. So nice job, everyone, on sticking it out. So yeah, we all are. We all are.
I wanted to do nap time. We just dim the lights and pretend we had a session, but Pete said we have to do it.
So we really, I think, have a good session in store for you today. This session has been held in the past, but even since the time last year, just in a one-year period, we have had 3 new versions of vSAN, and there's a lot of new interesting detail that impact things like the data path. And so we're going to explain that a little bit. My name is Pete Keeler. I'm a senior technical marketing manager in the storage and availability business unit, primary focus on vSAN. And I'm joined up here with Mr. John Nicholson. John, would you like to introduce yourself?
John Nicholson, Senior Technical Marketing Architect and Storage and Availability business unit. We need to shorten that somehow.
So we are not going to bore you with any basics of vSAN. We're going to make some assumptions that you already know that, and we're going to dive right into some of the details about the particulars of how vSAN works. So if there are some basics that you need to revisit, there are going to be some other session recordings available fairly quickly. And then we have some great resources online. storagehub.vmware.com is the primary portal for all things vSAN and all things storage and availability. That's where all of our information is posted.
SRM, vVols, core storage.
Everything. Let's see. Let's go ahead and move on to the really exciting disclaimer. Once again, nothing's going to be revealed in here that generally isn't already available, but you know the drill. So with that, I'm going to go ahead and hand it off to John, and he's going to jump right in.
All right. So vSAN is unique in a lot of ways, and one of those is that it's an object storage system under the hood. It's not a clustered file system. And this makes sense for a lot of reasons, because clustered file systems, as they scale and you design them, they tend to be really good at very small or incredibly large. And they tend to be optimized and have sweet spots around particular sizes of files. There's all kinds of fun limits. While object systems can fundamentally, as an architecture, assuming some changes are made, scale almost indefinitely. If you look at examples, Amazon S3, things like that, objects have an inherent flexibility and resiliency and distributed. So the vSAN data store, you'll see it as a single data store, but under the hood, it's actually an object storage system. And then those objects are broken down into subcomponents based off of the RAID or striping or its automatic chunking out of data. And so in this case, we've got a RAID 1 tree, and we can also see that we've set a stripe policy. And because of that stripe policy, we've got multiple subcomponents that are broken out across the various replicas. Also, since we're just using RAID 1, we want to have what's called quorum, make sure that we can figure out what happens if those 2 hosts that hold the data are separated, a split brain type scenario. We have got a witness component in this example. Now, those witness components are dynamically generated, so if you had a situation where you're using RAID 5, where you've got components split across multiple hosts and how the voting is done, you might actually see that witness component not be necessary. It would actually just automatically disappear. So don't freak out if you're looking at your environment and you see an object that doesn't have a witness. Now, going through what these objects are, we've got a couple just base ones that are associated. We've got the VM home objects. This is where the VMX lives, your basic configuration for the virtual machine. Also, we've got VM swap. So in the event you overcommit memory, you can actually, this is a place for that memory to go to disk in that case. Note, by default, this space swap is reserved on vSphere in general. On vSAN, there's an advanced setting you can set that will remove that reservation. That'll get you some space back. If you've got 500 gigs allocated of memory on a host, it's 500 gigs of capacity back for that host. And then lastly, we've got VMDKs here of the core objects. And so VMDK is your virtual machine, and those are objects. And what's unique here is because we're applying policies to different objects, and so our different RAID and all these characteristics we'll talk about, you could have different policies for each even individual VMDK. So maybe I've got a database volume that has a very low write, it's a OLAP workload. I could set a RAID 5 on it. Maybe I've got a log volume high write. I want to optimize that with a RAID 1 policy. You could do RAID 1. So you could have different policies, even as granular, not just as a VM, but an entirely a VMDK. And this really turns it around from the world of LUNs. We have a saying, LUNs suck, that we say quite a bit, where you have a data store and every VM inherits the policies of that data store. We're flipping this around. Instead of a bottom-up provisioning model, this is a top-down application VM-centric decision. And you know exactly what the current state of something is. Also, snapshots and snapshots of memory, those inherit the policies. They're separate objects, but they'll inherit the same policy, the base VMDK. So that way you've got a consistency there. So what does this policy framework look like? This is an example of storage-based policy management. So as we go through the various policies of vSAN, and we look at it, one thing to note is, as you're making it, we've got what are called what-if APIs. And so this tells you, based off of what you're doing, what are the implications of capacity. So if you're changing a policy associated with a group of virtual machines from RAID 1 to 5, or maybe you're setting object space reservation, which is then provisioning on or off, this is going to show you the implications of that. And these what-if APIs actually extend even farther across the platform to if you're doing maintenance actions, you're evacuating a host, you're putting a host into maintenance mode, things like that. We can now surface that information up. Because if you've ever worked with storage arrays and you did large-scale migration, sometimes the performance would deteriorate or be impacted. And maybe you only had a maintenance window that was 30 minutes long, and and if you're going to put a host in maintenance mode and it's going to move 20 terabytes of data, maybe you want to ask for a longer window. So rather than just yell YOLO in the data center and hit evacuate host. Who likes yelling YOLO in the data center? I do. That's what I do for every storage controller update. YOLO. Instead of just yelling YOLO and mashing migrate, now you can actually see what the implications of your actions are. So this should help with those cowboy operations teams rein in their behavior and start thinking about their actions before they do it. So going into the policies, let's talk about failures to tolerate. This is the core policy, and this tells you how many hosts you can tolerate a failure of. By default, it uses a RAID 1 mirroring construct. And so in this case, just very basic, we've got an object. It's split out to 2 hosts and has a witness. Now, this has been, obviously we've made some changes since last year. So the core failure to tolerate in a stretch cluster environment now becomes secondary failures to tolerate. That's the local site. And you have a primary failure to tolerate, which is the number of sites you can. So this is in a stretch cluster scenario. You can set either 0 or 1. So do I want to mirror to the second site or not? And then within that site, you can set, you've got your failure to tolerate, which you would in a traditional cluster of 0, 1, 2, or 3. Now note, if you set it to 0, that's a RAID 0 construct. So if the wrong drive fails, you're out of luck or going to backup. But typically, that's something that's reserved for imperial workloads, test dev things that you can regenerate quickly. Now, as you go to 1 or 2, you also have 3. And what these are doing by default with the RAID 1 is adding additional mirrors of data and additional witnesses for voting. So if we want to go to 2, for instance, that's going to have 5 hosts because we've got to have 2 extra witnesses and so forth. Now, number of stripes per object. Now, this is something that often gets misunderstood. Now, what this will do is this will try to find additional disk groups to place that data on additional capacity devices. It could be on the same host. In the example of the green mirror there, you can see that it found different drives in the same host to stripe across, but in the case of the blue copy, it actually chose different hosts. It's opportunistic, and that's one thing about vSAN is it's going to a certain degree, pseudo-random balance that out. It's balancing capacity on the back end. In hybrid, it's actually looking at cache hit ratios. There's a laundry list of things, and people always say, well, can I micromanage the placement? And I say, you're not smarter than the LSOM object algorithms. Those things have been honed by people for a long time. So also getting into this with the stripes, what are the benefits for this? So if you're in a hybrid environment and you have a high read cache miss rate, your cache isn't sized to handle all the reads properly, stripes can get you a little extra horsepower by splitting out and trying to reduce the hotspots on the back end. But these days, since most people are doing hybrid with large 7,200 RPM drives, that's only going to get you so much juice, so to speak. And I encourage you to make sure you're sizing that cache or shifting where most customers are towards an all-flash design. The benefits for striping policies in an all-flash environment is typically on the writes if you're maxing out the raw write throughput of your cache devices. But you can also improve that write throughput just by using larger cache devices that'll delay things like garbage collection, as well as just faster. Instead of using SATA SSDs, switch to SAS or NVMe, and as well as adding more disk groups in general. That tends to get you a lot of mileage. So there's a good blog post on this where we kind of explain this. In most environments, the default stripe of 1 is fine. This is something only if you're starting to see specific hotspots and things like that I would really go in and touch that much. Oh, before I go, one more thing to note is by default, we do what's called chunking. So if an object one of the components reaches 255 gigabytes, we're going to go ahead and split it out into another component. There's actually additional. Now, it's not necessarily striping. Those components could end up in the same disk group, the same disk even. So that's completely opportunistic where those go. But just for rebalances and things like that, we want to keep those component sizes. Fault domains. So what fault domains allow you to do is customize your vSAN environment to match the reality of the infrastructure underneath. Historically, with storage arrays, we'd have this 7 nines, 4 controllers, monster array, but you couldn't cut that thing in half. And the reality is I've got a drain pipe, and there's always a drain pipe that ends up in the data center, and it's right over where the storage array is. And it's actually never the clean water. It's always the wastewater. So, and if that, I don't care if this array, if it produces 7, 8, 9s, if that thing blows, it's gonna smell fun. So what this allows you to do is say, okay, I've got these things in my data center. I've got a rack. Maybe, I'm worried about someone tripping over the wrong PDU in the back. Tem, the destroyer of network uptime, is lurking in my data center. And I want to split vSAN out across multiple racks, multiple floors, multiple places on campus, things like that. And so what this allows you to do is do synchronous replication or even RAID 5 erasure coding across multiple areas. Now, the advantage with this is that this way I will know if I lose an entire rack or an entire floor, an entire cabinet, I still have that resiliency and that protection. Now for a number of fault domains, one thing to note is you follow the same minimums that you would have had for the given RAID type. So RAID 1, for instance, by default, you've got 3 fault domain requirements, so 3 hosts. In this case, you would have 3 fault domains. If you want to do RAID 5, which has a 4 host requirement, you now have a 4 fault domain. Also, thinking a bit further, you probably want to try to have 1 fault domain than the RAID type you're using. That way you can self-heal. If you lose a fault domain, there's a place to rebuild. Now, nested fault domains for stretch clusters has been a huge request. Anyone using stretch clustering today, vSAN or otherwise? We get a lot more hands in Europe, I swear. Fiber's like everywhere there. Yeah. I live in Texas. It's more than 5 milliseconds between all our cities, so it's not as common. So what previously vSAN with stretch clustering, all you could do was a basic RAID 1 mirror between the sites. And this worked, but the challenge was if you had a site turn into a crater or a lake, like my hometown, that site's not going to come back for a while. You're basically at a RAID 0 protection state on the secondary site. You can't support sequential failures. And people want to be able to support, the complete loss of a site for an extended amount of time. So we now have the primary failure to tolerate, which is 1, and that's going to be the mirroring between the sites. And then we also have the secondary failure to tolerate. In this case, we've set it to 2, and then we've set our RAID type for that, for handling of that to RAID 5.6. In this case, we'll have a RAID 6 within the site. And so we've got a RAID 6 within the site and a mirroring, so we could lose an entire site and then lose an additional 2 hosts and still continue to operate. So, you can do designs where you can tolerate potentially 75% of your environment simultaneously, lose an entire site and almost half of another site. That's 40% of our site. That's pretty powerful. Oh, one other thing on the I/O path specifically is how we do reads. So we do a read locality in stretch clustering by default. So we allow up to 5 milliseconds from a support basis between the sites. And the reason why we do that is the technology will work beyond that. It's just your users will grab pitchforks when you're write latency and waiting on that acknowledgement over 5 seconds. Your applications may not be too happy. So 5 seconds is that. Rather than read across that secondary site, we're going to read from the preferred site that's been set. So we actually do a data locality construct and always reading from the preferred site. Now, what if you've got really low latency? What if I'm, a couple microseconds between my sites, they're very close. In that case, there is an advanced option, the Worm DOM cache, and that will allow you to read from both sites and leverage the IOP capabilities of both. So the I/O path. Let's talk about writes first. So the writes come from the guest. The operating system issues a write, and that's going to go through your vSCSI stack, through your HBAs, and it's going to come into the host locally, and that host itself, where that VM is going to negotiate how to split or mirror erasure code that write. So in this case, we're doing a simple mirroring, and it's going to send those writes out synchronously to both of those hosts, and it's going to go to the cache tier. So in this case, we're going to wait for that to be acknowledged as persistently written to both copies. Important, we wait on both. And then that acknowledgement's going to come back. It's going to go through the vSCSI layer, and we're going to acknowledge the OS that your data's been written. So there's no situation where if one host blows up and one's still running or things like that, data gets out of sync or things like that. We're waiting on that. We do this very quickly. Well, let's look at how the reads work in a little bit more detail. So, the other thing to note is that write, once it's in the write cache, it's been acknowledged and we're done from the guest perspective. Now on the back end, that write will destage down to the capacity tier. And we do some things like we do some bit bucketing and try to group a bunch of writes together that are close. And there's a couple reasons for this. One, we're trying to de-amplify the writes to the back end capacity tier. We don't want to burn out, particularly in an all-flash environment. We actually want to reduce the endurance hit to that capacity tier, because those capacity tiers typically are a cheaper, lower endurance drive. Also, this allows us to optimize the writes to be more friendly and from a performance standpoint, because those capacity optimized flash drives don't always have the best in terms of write consistency performance. Those drives, you often see, have you ever seen a drive labeled read optimized? And thought maybe that's better than reads. No, the write optimized drive is faster at both. Read optimized is like saying my tires are parking optimized. They're bad at, I won't say they're bad at writes, they're not as great at writes. And sometimes you get really interesting latency out of them when you try to sustain a lot of writes to them. So basically you're being protected from that inconsistency and write latency that you'll see on those lower cost TLC drives in that perspective by that batching. Now reads. Reads are fun. There's a lot of places to read from. So we'll talk about hybrid, although this does carry pretty much into the all flash. So the read comes from the guest. Now the first thing that host is going to do is it's actually going to look locally in memory. We have a 1 gigabyte cache that is local to the host where the VM is running, that's shared across the VMs on that host. It's a DRAM cache. Memory is very fast. And it's read cache only, no writes, because it's obviously we care about persistence of data. Now, if it's local to there, we stop and we're done. So we've got a data locality construct for that memory cache that's local for that read path. Now, if it's not there, we're going to go look for it. And we actually split the reads out. So every other read is going to come from a different mirror in the environment, assuming you're using the RAID mirroring construct. And we balance those out. So as those come in, we're going to first see if it's in the cache. So in a hybrid environment, we've got 70% is for read cache, 30% for write cache. The read cache node is not mirrored. The write cache is, obviously, for protection. Now, if it's in the SSD, we're done. But if it's not there, we got to pull it from the magnetic tier. We got to rip it all the way from the lowest level, that spinning drive. Now, at this point, we're going to do some fun things. We're actually going to request, so let's say it's a 4K I/O operation. We're making a 4K read. We're going to make that read, but we're also going to say right after it, I want the whole megabyte of data around it. Because typically when you have a cache miss, you're accessing data that's been cold and isn't in one of the upper level caches, there's some proximity of data around it that's also probably interesting to look at. And we're going to move that all the way up into DRAM and then also put in the SSD and do a pre-warm. We also, as writes come in, a lot of data gets written and then quickly read and modified. We also pre-warm that data that's being destaged. As it's destaging, we're also moving it from the write cache to the read cache. There's a lot of things we're doing beyond your basic ARC adaptive read cache. There's been some really low-level caching algorithms to help deliver consistency of performance in this environment. Now for all flash, there's a common misnomer that in all flash we only read from the capacity tier. That's not true. Again, those reads can still come from the DRAM cache. They can still come from the write buffer. Maybe the data hasn't destaged yet. We're obviously going to read it from there. And then lastly, we'll go to the capacity tier, that backing in drive. We'll complete the read. And again, these reads are distributed across both copies. It's active-active. We don't have a silo that's not being used.
Yeah, and I think that's a really good point there. In that particular case where you have a high change rate of data in which it's being written and it hasn't gone through the point of where it's going to be destaged to the persistent tier, and that block is going to be requested on a further read, that it will fetch it from the caching layer.
And also, no question. Even blocks come from one copy, odd blocks come from the other. That's how it was explained to me. So makes sense. Now note in erasure code, copy, 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 that's it. Or missing copy, erasure code, recreate. So that's a little different there, but same but different. So again, going through the caching, we do the caching on DRAM, and we do this because memory is faster than the network. Network port to port, latency on a modern 10 gig switch, 350 nanoseconds. You might get 10 microseconds of TCP latency for now until you do an RDM transport. Networks are pretty fast. Now DRAM though is again a lot faster, your typical DRAM memory, and so there's that small local cache that accelerates that. We do not have the data follow the VM around like a lost puppy dog though. And the reason for that is when you start doing vMotions and you start doing DRS and you start doing HA operations, that causes performance to get really interesting. If you're doing, there's an expense, there's a latency and performance cost to moving data, and we don't want to pointlessly move data around. Now we do rebalancing and all kinds of things, which he'll get to in a moment. We try to be very efficient with that, because if we're wasting not only disk I/O, we're potentially exposing latency to the guest. We're also potentially wasting CPU on doing interrupts and moving data and things like that. One of the key design tenets of vSAN is consistency as much as possible, and also low resource utilization. I mean, we could build a 10 million per host IOP rocket, but if you use 98% of the CPU and you got room for half a container, it's kind of pointless. So there's a lot of balancing that has to go in. And so we want you to be able to leverage all the features and functionality of the hypervisor and be able to have DRS blasting at maximum, get that consistency. We also want to make sure the performance we're delivering from a consistency basis, you're able to meet your SLAs even in maintenance modes and things like that. So one of the steps in that direction is making sure that when it creates a new object, the LSOM will actually prefer to create that object not local. So you're getting, even though there may be a tiny amount of throughput advantage to reading from a local copy, not much, we'd rather you not be getting that initially and then lose it when a VM moves. Because you want to know your SLAs are working. Because if performance is consistent in your environment 95% of the time, that's great, but that's 1.9. And performance is effectively part of availability now. Because if the app's there but it's not responding on a performance, is it really up? It's not.
Yeah. So and really what this comes down to is we're treating the cluster in its entirety as a first-class citizen when it comes to storage. We know the benefits from clustering from a compute memory perspective, but then in a traditional three-tier architecture, you always had this thing that was hooked up known as a storage array in that shared storage environment, and you never knew where that storage was truly going once it left the actual HBA. This is treating it really as that first-class citizen to where we can create that consistent level of performance regardless of where the data actually lies.
That's the benefit of end-kernel architecture. We know what that storage is because you can get into fun race conditions. If the CPU is high and you can't access data and they're basically fighting, the scheduler can give priority to storage as needed. Checksumming, we do a CRC 32. We generate this as early as possible. So before it leaves the host where the VM is, we generate it. We verify it as late as possible when it gets to the host where it's being written. The checksum is not stored in the same block as the data. That would be silly. We want to make sure it's isolated. There is a slight amplification, although some significant performance increases were made recently to this in 6.6. So check that out. Note, if a block is impacted, we rebuild only that block. So this is not going to trigger a failure of a whole drive or anything more exotic than that. Also, if a block has not been read for 1 full year, we will go and scrub it by default. It's an advanced setting. You could drop it down to a month, but 1 year should be fine. So this combined with the fact that we're not doing holistic rebuilds, this helps mitigate concerns as you grow an environment about bit rot and things like that. Deduplication and compression. So this is where the I/O path gets really fun. We made some interesting design decisions because traditionally with dedupe, you've got two options. You've got inline, where every single block is done and it's fingerprinted. You do your deduplication, you do your compression. The challenge of that is you use a lot of CPU because you're inspecting blocks that have the lifespan of a NAT. They write, they're overwritten, so forth. The other option is post-process, but post-process requires a schedule. And I used to manage some storage arrays that required scheduling the stuff, and you'd have to figure out which volumes and what time of day. It was a mess. In fact, you end up reading these long stoic storage guides that say, yeah, only do this on full clone VDI and only if your users don't log in at night. We wanted to try to avoid the compromises on both sides of high I/O overhead, as well as also the challenges of high management overhead. So I'll get to the cost here in a sec. One thing also to note is how dedupe works internally is it stripes across those disk groups. So within a disk group is the fault domain and the dedupe hash domain. We don't do a global, and that's on purpose because we don't want a situation where you have a double puncture of that dedupe hash table and you corrupt everything globally. It's rather disastrous. We want a fault domain to truly be a fault domain. You take about a 20% efficiency hit on deduplication realistically with this in most environments, but data protection comes first. And since you can't identify where those pattern matches are going to be, we now just go ahead and stripe within that disk group. Now talking about the cost on the I/O path, the VM issues the write. The data is written fully hydrated to that write buffer. And this is the reason why we don't compress in the write buffer tier or do deduplication there, as well. It would give you a little more space. It comes at a cost of compute. And we do not want vSAN to be taking half of the host resources. That would be silly. So that data is written fully hydrated. If it's overwritten, then we never wasted compute. Next up, when we are moving it down to the capacity tier, it already had to go into memory. So it's already handy in memory. We're not adding any extra I/O hops. This is an inline process, but it's a delayed inline process. Now first we're going to perform deduplication. We're going to use a SHA-1 hash, which modern Intel CPUs can run 1 million of those in a second on less than a core, so very low cost overhead there. We're going to look for that. We've got some memory cache tables locally to accelerate the look of that cache lookup, or for the hash table lookup. And if it matches, we write a pointer and we're done. If it doesn't match, we're going to compress that. And again, by the way, that dedupe, that's not a 4K fixed block. It's very granular. It actually finds data. This isn't some 16 kilobyte or higher. It's more than just application binaries. Next up, we do compression. We use LZ4, which again is very, very fast. I know our friends at Google have done a lot of optimizations around that. And as we compress that data, we're going to look at it and compare it. If we can get that data compressed to 2 kilobytes or less, we're going to write it compressed. If it compresses poorly, if it's at, say, 3.5 kilobytes or higher, we're actually going to write it fully hydrated from the fully hydrated copy. And the reason why is, one, fragmentation on the back end. We don't want to have to get a weird extra I/O and CPU amplifications to mitigate that. The other reason is there's no point in wasting CPU rehydrating compressed data that compressed poorly. So all of these things, it goes into, I have this phrase I like to say, nothing is free. You're always trading and arbitraging something. So by using selective memory for the metadata lookups, in terms of how the data movement's structured, by avoiding fragmentation, and by making sure that data, how the pointers are written, they're directed in a very clean way. We're avoiding a lot of endurance overhead on the backend capacity tier. So while nothing is free, we are kind of cheating a lot of the traditional overheads here. Again, on that compression, we're avoiding some of the significant CPU overheads by not compressing data that was duplicate. We're also not compressing data that would have never, it lasted for 5 seconds. And we're not having to rehydrate data that compressed poorly. So by doing those 3 optimizations to the cost of compression, and most all-flash environments, customers can check that box for dedupe and compression, turn it on globally, and they're done. And so now you're not having to also have the management overheads and the costs associated with trying to figure out the schedules and say, all right, it's going to run at this hour, but my backups run at that hour, and then the SQL indexing runs at that hour, and people start coming in and making coffee at this hour, and they'll notice performance problems by this. So We wanted to try to make this a feature without compromise and not just a checkbox on our line card. And so these are all the optimizations done to the I/O path for this feature. Erasure coding. So we've got erasure codes, which I had someone come up to me this week and say, your RAID 5 and RAID 6 are on erasure codes. And if you really want to have that argument, you can have it with our CTO, Christos. He's got an excellent blog post. He's the CTO of storage. He's also a fellow at VMware and is much smarter than I am. But they are erasure codes, I do promise. So with RAID 5, we do a 3+1 stripe. That is fixed. If you really, part of that was people said, well, could it be something else? In theory, under the code, it could. But the reality is, from a QA test and just quality of feature, it's currently limited. If you have sufficient arguments, again, that's something to go argue with Christos. So from this, RAID 5 becomes your failure tolerate of 1 when you set this as a protection method. RAID 6 is an implied failure to tolerance of 2. So note, these are only supported on all flash. And the reason for that is we wanted to make sure that also when we deliver features, we don't deliver features that if you turn them on, there's a good chance of you having a bad experience at some point. Now with spinning drives, if you write data, you've got a lot of write amplification on this. And now you can try to hide that and mitigate that through write buffers and things like that. But the thing everyone forgets about is what happens when I have a failure with an erasure code stripe. I'm now amplifying reads, and at the same time I'm trying to rebuild data. It's very easy for you to have an amplification factor of 80% of the backend performance either going into the rebuild or just servicing existing read I/O that we're having to read the full stripe to recover the data. And so when you look at all these amplifications, even on data that's normally read cold, trying to do this on hybrid, it's not going to lead to the best outcome. And so our implementation of this is all flash, but it's safe spaving. I need more water here. There we go. Safe savings you can bank on. The data layout for the RAID 5, from an overhead perspective, a 20 gigabyte VMDK becomes 27 gigabytes instead of 40 gigabytes.
And so, John, I think actually that it's a good reminder here for everyone here is that these discussions around whether it be RAID 1 or RAID 5 and RAID 6 is applied at the object layer. It's not a matter of saying we're going to set a vSAN cluster at RAID 1 or RAID 5 or RAID 6. This is applied via a storage policy-based management on an object, whether it be a VM or a group of VMs. So you have that choice in that level of granularity.
And one thing that I love about the policy management framework is not only do you control it in the UI, but it also can be consumed by vRealize Automation, vCloud Director, OpenStack. We have a SPVM code for OpenStack, vSphere integrated OpenStack, vSphere integrated containers. These are all things that can consume this at a higher level. And so as we move to this, this software-defined data center, so we move to, I call it the policy-defined data center. In storage, we can deliver availability, performance, capabilities, also NSX. They deliver, performance, security, and availability and things through policies. They can all be consumed at a higher level. So the farther you get down that journey, this is kind of your baseline layer for that programmability of the underlying components. Data rest encryption. So this one's a fun I/O path. So encryption, we wanted to do data at rest, but the biggest challenge of data at rest is not breaking dedupe and compression. So we've got plenty of customers today that use high trust and things like that in guest VMs, and it does work. It's a good solution. They're a great partner. But they also want to do deduplication and compression. They want the safe efficiency. There we go. I'll say that. Works a lot better. So what we do is that the write comes in, and it gets to the host with the disk group. It's encrypted and written to the write buffer. So even in the buffers, even in the cache layer, the data is encrypted. Now, when that data goes back into memory to destage to the capacity tier, we decrypt it, we run our SHA-1 hash, we see if it's duplicate, and then we re-encrypt it to write it back down. So at no point is the data in a persistent storage device in an unencrypted format. Now, this is great because this really helps get you the safe space efficiencies you want. So I'm just doing it as a joke now. So From an encryption standpoint, also, this is software-based. This is leveraging AES functionality that is native to modern Intel AMD processors. And so rather than use self-encrypting drives, which is traditionally how this was done, rather than further sprawl our HCL of supported devices and add additional things that needed to be tested for, you can use existing customers today as they upgrade, can turn this functionality on. Now for vSAN, this is enabled globally, just like dedupe and compression. When you get to that set up my cluster wizard, there's a checkbox, turn it on. We also have a complementary technology called VM Encrypt, and there's a good session that compares and contrasts which one you would use. I believe Jace did that, so look at the recording on that. Note, data in flight is not encrypted. So data in flight is still not encrypted. Note, this is a common misconception on Fiber Channel, iSCSI, NFS. It's never encrypted unless you did an ingest-based encryption model. If you're looking for that, again, that's VM Encrypt, and I'd look for that session. Now, I mentioned this earlier, swap by default is thick, and this is the monitoring screen. You can look at your space savings and so forth. But if you look in here and you see that swap is getting high, you're reserving a lot of space for it, there's this advanced configuration you can set. Also, that's the CLI. You can also do it now within the UI. Also, if you go to Jason McCarty, his GitHub has an amazing amount of vSAN scripts for just all kinds of things, setting up a 2-node cluster, automating it. The hackathon this week, I think they produced some more fun code. So check that out. Snapshots on the I/O path. So historically, anyone like anyone who's worked in operations and sees this, they're probably having a seizure right now. Anyone ever had a performance problem from a snapshot? Okay, the rest of you either aren't in ops or you're lying. VMFS snapshots have a lot of challenges. In fact, there's a session from last year, if you can find the recording, called Snapshots Suck, where we went into a lot of depth on this. VMFS snapshots have a lot of performance challenges and overheads. vSAN, we do something different. We use an in-memory cache for the pointers. So rather than this choose-your-own-adventure book of hunting through the I/O path for where the data is, instead of losing 80, 90% of your performance as the snapshot tree ages and gets older and gets larger, instead we're able to look at memory and from that cache deduce where to go do that read block. Also, another change that was implemented just in general from vSphere 5.5 to 6, what's known as a helper snapshot, which was a place where I/O would get redirected during a merge. We no longer use those as of 6.0 even. And so instead we use a mirror driver. This came, same mirror driver, the reason why storage motions got a lot quicker sometime around the 5.0, 5.1 days is leveraged there. So we're double executing the write. So that way you don't get in a situation when you have runaway helper snapshots because you can't merge faster than the incoming write. So note there's a maximum of 31. While the normal KBs say don't leave VMFS snapshots open for more than, I think, 3 days, or in my opinion, is any longer than humanly necessary, a vSAN snap, you can leave one open for a week, and you'll still have to go through an I/O period for merge, so there still is that, but you're not at the situation to where you're frantically trying to close that as necessary. And I think I'm going to hand this over to Pete now.
All right.
Space savings.
All right, John, thanks. That was a really good overview of what vSAN does in terms of the storage I/O path when a VM is requesting a read or a write. But in vSAN, there's a lot of back-end activity that's also occurring. In fact, in any storage system, there is all sorts of different storage I/O activity that is going on. It's just that oftentimes it's not that visible. But we expose that to you in a number of different ways, and I'm going to show that in a little bit more detail here in a moment. So all of the data I/O path that John was referring to was really focused on that front-end VM traffic. And really what I mean by that is just a guest VM either requesting a read or committing a write. Now there's what we call a back-end storage traffic, and this is going to comprise of a number of different kinds of things. One is replica traffic. So if we are committing a write to one or more locations, which we would do if we would want that high availability and redundancy of that data, that means that there's going to be IOs traversing across on this east-west network, that being your network that connects all of the hosts to each other. Now there's another subset of data IO activity that is occurring, and this actually occurs in any sort of a distributed storage mechanism or solution where you have a number of hosts that you are taking advantage of the local storage devices in order to create this aggregate single data store, which is exactly what vSAN does. We have these data resynchronizations that can result from a number of activities, one being an object policy change. So imagine if you say, in the earlier example that John was showing, you would see that VM that you wanted to change from a level of failure to tolerate of 2 to 3. Then it has to make another replica of that object. So that's going to kick off that effort in order to create that additional object. You're also going to have some of that I/O activity, that backend I/O activity, if you have a full evacuation of a host or a disk group within a host. So a full evacuation of a host might be the result of you selecting the enter maintenance mode and choosing the full evacuation option. That data has to go somewhere, and that's going to be what it's doing there. It has to go somewhere because vSAN's primary duty is to maintain the compliance of the protection and the performance policies that you've set in the storage policy-based management. The other section that is really that kicks off any sort of backend I/O activity is rebalancing. vSAN is really smart in the placement of its data, and it's going to make sure that it can place that data in the right location, still adhering to the applied storage policy that you've set for that VM or VMDK. And finally, object and component repairs. This is in the event of some change in which it needs to repair some of that data, some of the components that comprise an object for one reason or another. And we're going to dive into a few more details in how this works here. Now, before I do that, just a quick show of hands. How many of you are running vSAN 6.6 or later? All right. Yeah, that's actually a pretty good showing. And the reason why I ask that is that these kinds of backend storage traffic activities have always existed in vSAN. But we've made significant improvements in vSAN 6.6. That version had a lot of improvements from an operational perspective, but we really looked under the hood in order to make the efficiencies of repairing and resyncing this data as good as possible. The fastest resyncs are the resyncs that never happen at all. So that was the goal. So the first enhancement here is this overall idea of repairs and rebuilds. Here we look at the repair and rebuild at a component layer. Again, an object is comprised of several components in order to see, and that makes up that copy of the object or replica. Sometimes you might see those terms interchanged on occasion, but they essentially mean the same thing. And again, this what is the driving factor here, again, is the storage policy-based management. You don't have to do any of this. When there is some sort of a host failure like we see on the screen here, vSAN's going to take care of that for you. This is really just an explanation of what is happening. At the time we alert you that something has changed, but it will take care of that for you. And we have a couple of different methods in which the repairs and rebuilds actually occur. If you have a host go down, and we're just going to use a host going offline as a very simple example. We don't know if that's a transient error in the network, or if maybe you brought it down suddenly for maintenance or host reboot of some sort. And so we don't want to be overly aggressive in the rebuild of the data that existed on that actual host. But after a 60-minute window, then it's going to kick off the repair process or the rebuild process of that data in order to satisfy the original compliance. And in this particular case, you see that VMDK object has a policy setting of mirroring or RAID 1 with a failure to tolerate of 1. And this logic works in a standard cluster as well as a stretch cluster as well. So we are topology aware in terms of that. So we have that understanding of the data placement. So one of the things that was improved significantly in vSAN 6.6 is this idea of enhanced rebalancing. Now, rebalancing comes in a couple of different forms. There's a proactive rebalancing in which you have a data placement across all of the hosts in the cluster, and vSAN's going to recognize when there is a difference in fullness of one of the capacity drives, and if it sees a delta of greater than about 30% or so, I think somewhere around there, then it's going to warn the user in the vSAN health service, and it's going to say, you know what, there's a little bit of an imbalance here. And then it's going to highlight a button that allows you to proactively rebalance that. It's not a necessary thing for you to do, but it's just simply alerting you. And some of those situations come into play in which you have, maybe you introduced a brand new host into a cluster, and you had all of these other hosts that were really full and a brand new host that didn't have any data on it. That's going to initiate and alert you to say, here we have an opportunity to spread out this data. Now, in a reactive rebalance situation, this occurs when any capacity device is around 80% or greater in utilization. And I say around 80% because it is sort of a soft number there. In that particular case, it's going to initiate a reactive rebuild, and it's going to attempt to move that data automatically without user intervention in an effort to place that data where there is more available space.
And that may create additional components if need be. So rather than if the component's a large component that there's only so many small islands to put it, it may cut it in half.
And so this is what this is really speaking to here is now that in vSAN 6.6 we can split that larger component into a smaller set of multiple components so that it can evenly distribute the data. And this really helps actually when we're looking at space utilization that may be reaching at a level that a user didn't necessarily want or maybe they weren't expecting. It's much more opportunistic at being able to find a good location for that data to live. So there was another improvement here in terms of rebuilds, and this introduced a new method in which the repair process is going to evaluate how it can rebuild. So under a normal failure of any sort, let's say a host failure in this example, after a 60-minute timeout window, it's going to look for a location in which it can rebuild that object in order to meet the initial compliance for that object. But now let's say, for instance, that host was offline for that 60-minute window, but it was brought back up during the time in which the rebuild was already occurring on one of the other hosts. Now, prior to vSAN 6.6, it would just continue to chug along and complete that rebuild on that new host. But the problem is that if there were a number of very large components that made up a lot of objects and a lot of data, that means that it was going to fully commit that effort to full completion.
Even if there's a low change rate. So even if only 5 megabytes had changed, it's just giving up on the old copy. So
now with the vSAN 6.6 and newer, it's going to, it has an additional method in which it's going to review and look for the best way in order to complete that resynchronization. If the host comes back up after that 60-minute window where the rebuild has kicked off, it's going to look at which option is going to be faster, just updating the data that was on the host that went down, or completing the resynchronization process. So again, this is really about reducing the amount of resynchronization in the first place that's going to benefit ultimately all of your VMs and reduce the amount of east-west traffic that is running across your network. We introduced a new feature in vSAN 6.6 called a partial repair. And the best way to explain this is really by showing this example here in which we have a VM that has a VMDK and it has a failure to tolerate policy of 2, meaning that there's 3 copies of data, that it can survive 2 failures of any sort.
And this is the RAID 1 protection method, not RAID 6 here.
That's correct, yeah. Thank you for pointing that out, John. Now, in this particular case, if we have 2 hosts fail, we still have availability for the actual VM. We have 1 remaining copy up. But again, our effective failure to tolerate is 0 right now. We can't survive another host going down. That VM would no longer be available. You wouldn't lose the data, just those VMs wouldn't be available. Now, with this partial repair, this is going to be, think of it as an opportunistic repair. This is going to look for available space and initiate a repair process. And if it can increase the effective failure to tolerate policy from 0 up to 1, it will. Even if it's not going to be able to complete the full failure to tolerate policy of 2. It can't do that right now simply because there are not enough hosts available in the first place. And in versions prior to vSAN 6.6, it would want the ability to have full compliance before it initiated this repair. And so this is really looking about how can we do as much as we can in order to kick off that repair process. And if you noticed here, actually, and I'll back up this one slide, we saw 3 replicas and 2 witness components. And the reason why there were 2 witness components is the idea is simply to establish quorum. And when you're in an effort to avoid split brain scenarios, you always want an odd number. Yes?
Just a question regarding the partial repairs maybe behind that. If it's going to try to realize that if we're in an XMT0 situation, it needs to get it back up to XMT1, regardless of policies 2 or 3 or whatever, is it also going to be cognizant and aware of the remaining overall capacity on the cluster and not completely fill up what's left on that data store in its efforts of trying to.
It's not going to fill up a disk group.
Yeah.
So the disk groups are fundamentally the pools, so to speak. So, yeah.
So in this particular case, we notice here during the repair process, notice that one of those witness components goes away. It's replaced with a replica object. We give priority to rebuilding the data first. And this witness component is a really small, tiny object. Or
4 megabytes, I think?
Yeah, it's really, really small. So we know that that's much easier to reestablish than the actual data itself. Now, once we bring another host back online, then it can establish that second witness component, and now we're back up to the effective full compliance of FTT equals 2. And again, this also works in non-stretch clusters and stretch clusters. It's especially beneficial in stretch clusters as well.
Yeah, from stretch clusters, it will always try to rebuild from the local copies if possible, rather than generating WAN traffic over that replication link.
Yeah. We have about 5 minutes for a little Q&A. Should we kick that off, John?
Yeah, let's go to QA.
All right. If we could have you step up to the microphone, possibly. This session is being recorded, so we would like to capture the questions.
Hi. What happens when that replica object comes back? Does it trigger a rebuild back?
When the object comes back on and it's fully completed the effective resynchronization, then it's going to get rid of that data.
It's going to delete it in this case because we're back to policy compliance. We don't need it. It's old. It's stale. Done.
Hi guys, great session. I'm profoundly dumbfounded. Can you change the time to do the rebuilds? Can you speed it up or wait in the case that you know it's coming back?
So there's a couple options here. So first off, we mentioned that 60-minute timer. That's for what's called all paths down, which is basically we think this thing's missing. We don't know if it's actually dead. We get a hard PDL code, like a drive dies, and we get a PDL code from the controller, physical device lost. We know it's dead, Jim. It's not coming back. It's going to immediately initiate the rebuild. Now, a host being gone could be network, could be someone rebooted it. Who knows? You can adjust that APD timer, but 1 hour is pretty sane in our opinion. That said, yes. There's also from resynchronization now in the UI with 6.6. If you want to dial the prioritization of I/O for resync, you want to throttle resync because you're not as urgent to repair. You're more concerned about impact on production. There is a dial now.
Thanks, big fan.
Nice shirt.
Question about the intelligent rebuild. If I have a cluster that has a lot of data at rest on it, I lose a host, 60 minutes go by, Combi kicks off the rebuild or resync. The host comes back. Now I've done a real good job as an admin and ignored the health check item that says after one host loss you're at a little overcommitted on your data store. If let's assume that the host comes back after that 61 minutes, all the objects are invalidated. vSAN is going to start looking at and seeing, okay, do I need to continue the resync? Can I pick the object off the host that came back? Is it also going to say, well, the hosts that came back, those objects aren't any good, delete them and use that space? Or am I going to run into running the needle at 99% of consumption, have a real slow resync because I have free space I could use for the resync and it's not going to consider it? How does that behavior work?
So if there is an opportunity in which you have an existing copy of components and then that additional host comes up, it's going to initiate those copies right away. And then if this host comes back up, then it's going to evaluate which one is in a better state to full completion. And then it's going to make the decision at that time. Just right at that time, it's going to do an either or.
Okay, so it'll leverage the used but free space from the host that comes back.
It should delete the invalidated copy, I believe, immediately.
Okay, and then leverage that host.
I think there's a grovel process, like a couple minutes maybe. So.
Sure. Okay, great, thanks.
Mm-hmm.
Question around the compression and dedupe functionality. If I recall correctly from the slide, that's controlled within a disk group level.
It's enabled globally.
It's enabled globally,
but the deduplication collision or how it detects SHA-1s is within a disk group.
Within a disk group, yeah. So from a optimization standpoint, if I wanted to create a vSAN cluster, for example, where I wanted to have as much deduplication as possible, I'd want to architect to use larger disk groups as opposed to having.
Yeah, obviously you'll get more dedupe with one or two disk groups versus four or five. Note, you do get more performance from more disk groups. In fact, that's one of the easiest ways. So as a middle ground, I'd shoot for two disk groups, just because two disk groups in a lot of cases doubles your performance without necessarily going to 4 or 5. So, and if you look at the new write cache sizing recommendations, we're not recommending 10% anymore. We're recommending basically a total amount of cache in the host. And the most extreme recommendation is 1.6 for 100% write. You're trying to push 80,000 IOPS, no reads, things like that. So. And
there's also a falling rate of increase in efficiency with that dedupe as you increase that space, because you can only dedupe that single block so many times. So
the metadata overheads eventually creep up on you.
Yeah,
sure. Okay, thank you. Appreciate it.
Couple of questions around stretch clusters. 2-node stretch clusters.
Okay.
One, what happens with the 2-node stretch clusters when witness goes down and subsequently one more node goes down?
So what will happen if you don't have quorum anymore? is it will cease I/O to that object. It will split brain protection will kick in, and so the VM will basically be unable to process I/O at that point. Okay. Now, if that second host came back online, so let's say the witness failed first, then the other host went offline. That other host comes back online. They'll check their sequence numbers. No, okay, we're in sequence. Reestablish quorum. At that point, the VM could resume I/O processing.
So, while all of this is happening, no vCenter access. How would that play out?
With no resync?
No vCenter access. So with 6.6, I believe the dependency on vCenter reduced quite a bit.
So the vCenter, yeah, so with 6.6.1, there was a slight, in 6.6, there was a slight dependence on vCenter on how unicast host discovery was done. And that was all tied to if the vCenter was being recovered or was being redeployed. That was mitigated extensively in 6.6.1. If you go to storagehub.vmware.com, look for the multicast removal guide, and I actually outline exactly what those dependencies were at a lot of granularity.
Yeah. One more question.
Great session, guys. Thanks. One thing I was just curious about with the changes on the hardware layer and various different advances that we're seeing in that space, could you maybe tell me a little bit about and this might be futures, I'm not sure, but I'm wondering about the impact of emerging technologies like fiber channel on token ring, things like that.
I mean, fiber channel over token ring is such an avant-garde technology. It's so far advanced. I mean, our office of the CTO might be able to comment on that, but I mean, it's such a civilized underlay at that point, so thank you for that question. By the way, again, make sure to fill out your surveys, guys. Check out the Virtually Speaking podcast. We have a lot of great content there. He's wearing one of our nice shirts, modeling it.
There you go, right there. And again, yeah, if you can, please fill out your surveys. We really appreciate it. We look at it, and we'll certainly look to improve anything that we can. So, thank you.